Hi, welcome to the Signal Path. In this episode, I have another product review for you guys, and this time we're looking at a brand that I have never owned and I've never had in the Signal Path before, so I'm quite excited about it. We're going to take a look at the Siglent SDG5162 that you can see here, and there's a Siglent STM3055A, that's for later. I'll talk about that. But we're going to go ahead and take a close look at this, and not just look at it on its own, but I'm also quite interested in contrasting and comparing it with the Rigol DG4162 because they have essentially the same specification and their price is a little bit different from each other. The Rigol one is a couple of $100 more expensive, and I'm curious about the performance of this and some of the functionality and some of its features. So I'm going to dig into this and also give you a teardown, take a close look at it and see what it can do. I'm quite excited, so let's get started. Well, before I tell you about the Siglent SDG5162, you may have noticed that I also have a Siglent STM3055A, which is a 5.5 digit bench multimeter that Siglent has released, and I believe this is one of the very first units in North America. I just got this yesterday, so I haven't had much chance to play with it, but this is one of the next items in my review batch that I will do a teardown and full review of it. And since you're looking at it right now, if you have any suggestions or ideas, any particular tests you'd like to see with the STM3055A, please leave it in the comment section for this review, and I will take it into consideration when I go ahead and tear this down and review it. But so far it looks really promising, and for the price, you know, it looks pretty good. So anyhow, we'll come back to that another day. For today, I wanted to show you the SDG5162. I'm sure you've seen the front panel of this many times, so I'll focus on some of its functionality and some experiments. But you can see that the way the layout of this is done, initially I was a little bit skeptical because I was worried that it would be difficult to set all the different settings in terms of choosing the waveform and the different types of attributes that you want to give it and switching between different parameters. But actually it has a very logical flow to it. You know, you have the waveform button and the parameter button and the channel button, which is really all you need. In the waveform button, obviously you choose the type of waveform. In the parameter, you set the parameters for the waveform, and in the channel, you set the channel properties by turning it on and off and so on. So it actually is pretty straightforward. And these are the main buttons that you'll be essentially using most of the time, and they lit up. The main buttons all light up, so you know which one you're pressing. They're a little bit dim. I would have liked perhaps a little brighter, but other than that, it's pretty good. I like it. I think this is running the latest firmware based on what I checked on the website. I don't really like the color schemes of the screen so much, but other than that, I think they've done a good job at keeping a very consistent GUI and a consistent way of reaching different parameters. Now, the shape of this unit, all of the Siglent, this type of instruments that they sell, they have the typical, you know, front and long chassis type, which is a very different approach than the approach that Rigol has taken. For example, here I have the Rigol DG4162, which is spec'd the same as the Siglent SDG5162. They both have the 160 megahertz, 500 megasample per second specification, but they have gone through a very different type of essentially instrument shape. As a result of that, this obviously has a much bigger screening, has many more buttons in the front. It has much more area to work with because it has a much flatter surface, such a lot deeper. It's a very narrow instrument. As a result of that, you know, I like big screens. I'm sure a lot of people like to see a bigger screen. You know, the disadvantage of something like this would be that it's not stackable. And other than that, there is really nothing that I dislike about this type of design. But you know, it makes it sometimes difficult to put things on top of each other, like I have, for example, in the Siglent. But other than that, you know, I think that if you really want a big screen, obviously, then you're limited to the DG4162. But there's some interesting performance parameters for the Siglent unit that I like to go over. Other than that, you can see that the two outputs are in the front. Now, this also has the counter input because this has a frequency counter, just like the Rigol one that has a frequency counter, but the input is in the front. So it's a little bit more convenient sometimes if you want to quickly use a counter. The counter for the Rigol unit is at the back of the unit, but at the same time, Rigol then gives you both of the sync outputs, which can be beneficial for some time when you're doing synchronization with the oscilloscopes or with some other circuit and so on, for analyzing waveforms that come out. So it has this advantage. It would have been interesting to see if you know, to me it looks like they could have fit another connector here and squeeze this a bit closer together, but they've gone a different route and putting the counter at the back. So let's take a close look inside this unit and see if the construction has changed or improved in the past year or so since somebody else has taken a look inside this unit. I'm not going to go too much into detail. I just want to give you an overview, take a quick look at it and compare it to the old one and then go from there. Here we have taken the unit apart. This assembly is very straightforward. The back just simply comes off, and interesting enough, my warranty sticker, I didn't leave any residue, it just kind of peeled off on its own. But anyhow, and you can see that the construction of the case has been improved, I think, and it's nice. It doesn't have the poor weld joints anymore. It's nicely crimped in place like so, and it's fairly light. It's made of aluminum, you know, typical straightforward case that you would find in an instrument of this grade, and I'm pretty happy with it. And if you look at the main chassis itself, it doesn't seem to have that rust problem that the old units have, and it has now a shielded cover at the back here, this conductive foam to better shield the chassis together and make a good conductive ground, overall ground to the body. So I think that's pretty nice, and everything is nicely put together. I think that they've improved the construction of the chassis. You can see it doesn't have weld points anymore. They're all crimped kind of together like this. So looks pretty good. Now we can take a closer look at the boards themselves. Just like the old units, the construction is separated depending on the function of the board, and you can see the power supply is still on this side, and they've gone through a lot of trouble making sure that all the cabling is nicely tied down. You can see that this is now a very refined design. They've been making this for some time now, so the construction mechanism has been really well fine-tuned, and it looks pretty good. You can see that they've gone through a nice bit of trouble making sure that all the cables and everything is nicely crimped down in place, and everything is together. There's nothing, you know, if I shake this, nothing is vibrating in there. All the cables are nicely tied down, which is great. And they've also made sure that any component that could potentially come off due to vibration has been glued down. You can see the main cap has been glued down on the side here. Lots of generous amount of glue over here. You can see that they have also applied some of the silicone glue onto the cables that go from the BNC connectors at the back to the main board, so that they don't come off. And even the ribbon cable that comes from the display is actually taped down to the connector on the PCB itself. They didn't apply the glue anymore. This is a tape that is on top of it, making sure that this is connected to the board fairly well. And if you ever want to take this off, you can peel the tape off and then it will come back off. So really nice construction. And you know, if you look at something like this and you open something like this, I don't see any particular problem. I think the design is on par with anything that, you know, Tektronix or Keysight or LaCroix, and I think LaCroix actually rebrands this particular item. You know, they would put out this fairly straightforward, nice, clean layout, good soldering. Everything seems to be in order. So I'll go briefly over a couple of things here, but really I'm not going to go into too much detail because you've seen this before. So a couple of things, interesting thing to note is that you can see that the connections for Ethernet and GPIB are still available in this chassis. They're covered up with the back sticker, of course, because this unit does not support that. It only has the USB connector itself. And I believe that if you buy the LaCroix rebranded version of this, that there is an extra board installed here. You can even see the footprint is available here. This footprint here presumably supports another board, which then has the Ethernet as well as the GPIB controller already built onto it. So I think that's possible to retrofit this. I don't know if the firmware would support it or not, or you need to upload a new firmware to it. But everything else is the same. You can see that the buzzer is all the way up here. It still uses the same analog devices, Blackfin processor, you know, SRAM, flash, the CPLD from Lattice CPLD is here. The USB, Ethernet, all those controllers all in one is located here. So this is a purely digital board which interfaces with the computer as well. And you can see it's fully separated from the mixed signal board here via this ribbon connection. And of course the main mixed signal is the board that receives and puts out triggers and 10 MHz references and so on and on. And here's the main FPGA that is connected to the dual DAC here, which is a 500 megasample per second 14-bit DAC. There's two of them in here. You can see the interface memory to the FPGA on each side for each channel. And if you look very carefully here, I will zoom in a little bit more and you can see the traces coming out. And once again, what they've done here is that they have gone ahead and kind of scraped off the part number of the EEPROM that programs the FPGA. Presumably they do this so that you don't know what part number this is, so that you can't read off and steal the firmware, the bit file that is inside this EEPROM that programs the FPGA. Now, you know, people say if somebody really wants to do this, this won't stop them, and that's true. That if you buy one of these units with the intention of just simply finding out what's in here, you could unsolder this and dissolve it in ACID and eliminate this, and then read the code of on the IC. Possibly that's one way to figure out what's in there, and then you can then take another one and read it off. But that would mean that you would have to destroy the unit, or even more than one unit to do that. Really, they do this so that people wouldn't be able to easily do it. If somebody really wants to do it, they can go ahead and do it. It's just to prevent the opportunity of having a straightforward access. That's really all that they can do by doing this. The other thing is that here's the crystal reference, which is a reasonably low phase noise reference for the whole clocking scheme of the DAC itself, so they've gone ahead and used that. One other thing that is a little bit unusual is that if you look here, the isolator ICs here that separate the digital board from the mixed signal board seem to have some residue of flux on them, which is strange because I don't see this residue of flux anywhere on the board, almost as if this was added afterwards by hand and not through the reflow soldering of everything else, which is a little bit unusual. I'm not sure why this is the case, but this can be easily cleaned up. Probably I'll clean it before I put it back together, but everything else looks very nice. You can see a whole bunch of the DC-DC conversion power supply and so on at the edge of the board, which of course that's where you'd want to put them. You can see to put them as far away as possible from the analog outputs, which are on that side of the board. So fairly nice. And then if you can go ahead and take a closer look at this part, you can see the two traces that come out of the DAC, the two differential lines, and they go through this pair of relays, and then they go into two perfectly symmetric portion of the PCB which handle all the analog components. And these things obviously have to be symmetric and the same, so that the signal integrity and the bandwidth and the delay and everything that you would expect through these parts of the circuit will remain the same. And these, of course, these two cables that you see here are channel 1 and channel 2 outputs. Now, these things do support a shield cage to be put on top of them, like a can, but they're not populated. You can see the footprint is present, so you could potentially have a can on top of this, but they're not there for whatever reason. Probably they either didn't need them, or they figured it wouldn't make much of a difference, so they avoided it. But yeah, anyhow, if you really wanted to, I guess you could go ahead and add that. There's a whole bunch of relays here, and these relays will switch in and out different types of, depending on the waveform and the DC offset and so on. They will kick in and have various functionality in order to achieve the type of waveform that you want. And you can look at the block diagrams and all that. It's not that critical. And other people have gone through this, so I'm not going to spend too much more time on it. But you can see the structure fairly easily. You can follow the signal path and everything very easily. The power supply itself is very nice. I think it looks good. The layout is nice, and then on the other side, Dave has looked at it, and he's pointed out a couple of issues for the old one. Not too serious, but overall looks good. Everything is nicely glued down. It does have a hard power line. You can see that this flyover cables is to completely disconnect the power from the power supply, so there's no standby power supply, unlike the Rigol one, which has a soft power switch. There's a fuse at the left here with a cage for the fuse, and some protection circuitry at the input. There's a PCB mounted power connector here, nice earth ground to the chassis. Yeah, it looks good. I don't think there's any particular problem with it. You can see that also there's one fan at the side here, which will, if I'm not mistaken, probably either blow air in, and I cannot tell which direction the air will flow, but most likely it will either probably blow onto the FPGA to cool it down, and you can see that the airflow will be supported. It will flow through the power supply itself, and there's nice open space here to allow nice airflow through everything. So looks good. At the back, if I can flip this thing over, you can see at the back of the PCB is exposed both for the digital and for the mixed signal board, and everything is pretty straightforward here. It's the back of the FPGA with all of the coupling caps that you would expect for the FPGA. This is the JTAG connector, which is visible on the other side, so you could potentially program the FPGA yourself, although I don't know what changes you would want to make there. And yeah, looks pretty good. Mostly passive on this side, nothing too fancy. And I think that my point of generally doing this to show you that the construction is very good. It is nice and refined, and now they really know what they're doing. So if you look at this, it is just as good as any other manufacturer. So I'm pretty happy with the construction. I'll just go ahead and clean up a little bit of the flux on this side, and then yeah, we can go ahead and turn it on, update the firmware to the latest version, and then see some of the unique features of this particular unit compared to its competitor like the Rigol 4000 series, which offers the same specification, and we can see what we can do with these unique features. So for the purposes of doing some comparison, what I've done here is that I've taken both the output, the very channel 1 output of the Siglent SDG5162 and the channel 1 output of the Rigol DG4162 at the same time. I'm going to look at both of these, both in the frequency domain and in the time domain. And in order to do that simultaneously, I've taken each of the outputs and I've put them through a 50 ohm splitter. Now remember, these are resistive splitters, so they use resistors as opposed to reactive components like inductors and capacitors to split the signal. As a result, they are very broadband. They start splitting the signal starting from DC, and these are actually really high frequency ones that I'm using here. But anyhow, the disadvantage is that you lose 3 dB of power inside these as well, because they're resistive, so the resistors dissipate half the power and the other half is coming out from each one. So the loss from the input to each of the output is 6 dB and not 3 dB. Anyhow, so you have 2 of these. So this is coming from Siglent, this is coming from Rigol, split into 2, and one of the output goes onto the analog input of the Tektronix MDO, and the other one goes to the RF input of the Tektronix MDO. Similarly, for the Rigol one of the outputs goes onto channel 3 of the Tektronix MDO, and the other output goes all the way up there to the Rigol DSA1030A. And I'm using this again because there's only one RF input, of course, for the Tektronix MDO. So this way we can look at really everything simultaneously, including linearity. We can look at the noise floor, we can look at different types of intermodulation products and the pulse shape and so on. We can really get a close look at everything. So I can go ahead and set these guys to output the same waveform, just to start with. So here the Rigol is set to 1 kHz. Let's keep it at 1 kHz, and I can go ahead and change the amplitude. You can keep it at 5 volt peak to peak, that's fine. And then I can go ahead here and take the Siglent unit, do exactly the same thing. You can see that the waveform is already selected standard, so it always shows you the little preview of what you're doing. And this is a live template, so it moves around and changes as you change the signal and everything, so you can get a quick idea of what it is that is going to come out. So then we're going to go to the parameters, and I'm going to change the output. We're going to keep it the same, and I'm going to change the output to 5 volts peak to peak, just like we have there. So now if I go under channel 1, you can see that this is by default in 50 ohms, and if I go ahead here, I can do the same thing. And here is a little bit more complicated to do that. You have to go under utilities, and you have to go under channel 1 setup, and then you have to go under high impedance mode, and then you can go into 50 ohm. I wish this started at 50 ohm because most of the time that's what you'll be doing anyway. But anyhow, there we go. So it's all done. So I can go ahead and enable the output. There it is. The output of this guy is enabled. And similarly, we go ahead and turn this one on, and the light will turn on, meaning that the output is being applied. So now let's go ahead and take a look at the scope and set it up so we can see the waveforms. Here we go. So now that both of the outputs are enabled, one thing I didn't mention is that, remember that what I have done is that I have actually locked the 10 megahertz reference of both of these units together, because if you don't do that, each of these waveforms are generated with a different time base, and of course they're not going to be 100% correlated to each other. So you need to make sure that they're synchronized so that one waveform isn't continuously moving, rotating the phase with respect to the other one. This way they're at exactly the same frequency, being fed from the same reference for the internal PLL. So it all makes sense. Now let's move the camera a little bit over so we can take a closer look at these waveforms. So now here channel 1, which is yellow, is coming from Siglent, and channel 3, which is pink or purple, is coming from the other unit. So we can go ahead and do some basic calculations on these. Here we go. So you can see that by looking at the information underneath here, essentially these waveforms are, at least to the naked eye, almost identical. They have the same frequency, they have the same peak-to-peak value, and because we can control the individual phase of these from the instruments themselves, I can go ahead and change the phase of this signal directly I can go ahead under phase here and I can rotate the phase, and you will see, you can see on the scope simultaneously. Let me make this every 10 degrees. You can see I can easily align the phase because they're locked together and put them essentially on top of each other, and here you can see perfectly, you know. There you go, I just made the other one completely disappear behind the other waveform. So you can see that they're really close. But what I'm interested in taking a look at is also not just the way they look at with the naked eye, but also the spectral content in terms of the linearity of this signal. So let's go ahead and change the frequency to something that's slightly more challenging for them to meet the THD. So I'm going to go ahead under waveform, and I'm going to under parameters and then change the frequency. Let's go at 50 megahertz, which is about a third of the maximum frequency, and so on. So I can go ahead and 50 megahertz. There we go. And I can go ahead do the same thing down here. Of course, now they're not locked together because the frequencies are totally different now. So I can go ahead here under sinusoid and change the frequency here to 50 megahertz as well. There you go. Now we have 250 megahertz sinusoids. You can go ahead and, I'm going the wrong way. Here we go. Oops, that's my mistake. One of them is set to 5 megahertz. I can fix that. 50 megahertz. There we go. Sorry about that. There you go. You can see now. Now one of them is, here's something interesting to watch out for. So I have, even though these two units are locked together, they are not completely perfectly locked. Their phase noise of the signal generated from each of these two units are uncorrelated. So what you see here is that by triggering on channel 1, by triggering on the Siglent unit, you can see the phase variation of the Rigol unit with respect to the Siglent unit. This doesn't mean that the Rigol unit is not clean. It just means that they have uncorrelated phase noise and jitter with respect to each other. If I go ahead and change, and you can see a little bit better if I zoom in, if I go ahead and change the trigger source from one to the other, we go on the trigger menu, and I change the source from channel 1 to channel 3. This is a little bit touchy. There we go. You can see that now the other waveforms looks jittery. So they are really essentially the same. This is an artifact of the way these signals are triggered, and nothing more than that. So we can look at the spectrum of these individually if you want to see jitter comparison, but they should have the same jitter because I believe they use this very similar PLR architectures. So now let's go ahead and let me go ahead and disable the Rigol output for a second, and let's look at the spectrum of the signal so we can do some comparison. So the signal is too big here, so let's go ahead and set the reference amplitude to 10 dBm. There you go. It's still a little bit too high. Let's make it 20 dBm. There we go. And we can go ahead and change the frequency. Start from and stop at, let's say, go to the fourth harmonic, which is 200 megahertz. Here you go. There, now you can see the fundamental second harmonic, third harmonic, and the fourth harmonic, which will be at the edge of the screen. And we can go ahead and reduce the resolution bandwidth just a little bit to, let's say, 50 kilohertz, and then we can get rid of everything. There. So now what you're looking at is that you're seeing basically the very first signal at 50 megahertz with 11.1 dBm, which corresponds to 2.5-fold peak to peak. And something else to notice is that both of the instruments, the output amplitude signal dropped a little bit as increased the frequency due to various losses and so on. But that's not so important at the moment. But yeah, we have 11 dBm is the fundamental power of the first tone, and then we have minus 30 dBm as a second harmonic and minus 28.5 dBm for the third harmonic. So the second and the third harmonic are actually quite close together. They're very similar, and this is to be expected. You know, this is a single-ended output, which means that the THD is dominated by roughly by both of them and not just one of them. But you can see that we do have quite a large, about more than 40 dB of THD between these two tones. Maybe about a little bit less. Maybe I should say 40, a little bit less than that. But anyhow, it looks pretty good. It's a fairly linear sinusoid signal. So I can do exactly the same thing, and I can look at this on the Rigol unit. So here's the same signal now looking at the Rigol unit, and if you look at this, it's quite interesting because you can see that it has exactly the same power at the fundamental, 11 point something dB, that the power on the from the Siglent is 11.1, it's about the same, but the second harmonic is a little bit lower. It's about a couple of dB lower in terms of power on the Rigol one, but the third harmonic is higher on the Rigol one. So the THD actually ends up being about the same. And this is to be expected because they're using the same type of hardware to generate these tones. And what we can do as an experiment is that we can go ahead and max out and keep increasing the output power of these units to as much as we can, and just to establish a linearity performance comparison between these two units. So what I'm going to do is I'm going to increase these to the maximum they can do, and then we can take a look at the THD on each of these units. Let me go ahead and do that and show you. I'm not the reason I turn the camera off when I'm making the changes, because I know I don't want to waste your time showing you those little changes. I'm sure you're more interested in the result anyway. So let's go ahead and try that. So here I've maxed out the units at the highest frequency and highest amplitude they can provide. Now here's another thing that's interesting is that the Siglent SDG5162 can obviously go to 160 megahertz, and it can do 1.5 volt peak to peak, and just make sure you can see that. There it is. So it can do 1.5 volt peak to peak at 160 megahertz into 50 ohm, whereas the Rigol one limits you to 1 volt peak to peak at 160 megahertz into 50 ohm. So in fact, it appears that the Siglent one can give you more signal swing, which can be quite important depending on the application that you're looking at. So now I've turned them both on, and we can look at it on the oscilloscope, and the divisions on the oscilloscopes are the same, and everything is the same. All the settings are exactly identical. All the ports are set to 50 ohm, of course, and you can see clearly that channel 1, which is the Siglent unit, has more signal swing. Again, the jitter, don't be misled by the jitter. The jitter obviously appears to be more at higher frequencies because it occupies a larger portion of the period. The jitter is constant in RMS seconds, but it will be a larger portion of the total width of the signal, the total period. That's why it looks to be worse at 160 megahertz. But in reality, the jitter is actually the same. So you can see now, again, this doesn't mean that the Rigol one is jittery. It's just that I'm triggering on channel 1. But you can see the channel 1 is now giving me 780 millivolt peak to peak, whereas channel 3 is only giving me 500 millivolt peak to peak. And remember, there's some losses in the cables, and there's 6 dB of loss in the splitters because they're resistive. So now I can also go ahead and look at the spectrum of the signal in a similar way. So let me go ahead and turn channel 3 off and enable the RF input again. Let's take a closer look here, and I can go ahead and change the range in order to make sure that we're looking at the signal all the way to its third harmonic again. So we can start at, there's nothing below, there's actually only very, very little signal here. So let's go ahead and start at, let's say this is 160 megahertz. Let's go ahead and start at 100 megahertz, and there we can stop at about 3 times that. Let's stop at 500 megahertz or so, like so. There we go. So we can see our signal here, and we can see some other spurious tones that are generated by the analyzer, as well as some of it is generated by the Tektronix MDO, but most of it is coming from the Siglent unit. So now you can see that the power of the main tone is at at 0.8 dBm, and the biggest harmonic that I see here, at least in this band, is at minus 25 dBm. So it still has a reasonable good THD, about 25, 24 dB of THD, which is pretty good depending on what you're doing at 160 megahertz is reasonable. Now we can go ahead and look at the same signal. Remember, the output power of the Rigol is going to be a little bit lower, so we can go ahead and do the same thing and take a look at the signal from the other spectrum analyzer. So here's an interesting result. The Rigol generator is much cleaner in terms of spectral purity at 160 megahertz. I'm looking at exactly the same span from 100 megahertz to 500 megahertz, and the output power is minus 2.33 dBm. It's less, remember, because it only goes to 1 volt peak to peak. But the second harmonic is sitting at minus 53, so it has quite a bit of total harmonic distortion. The signal is quite clean. Now you may ask yourself, well, that's probably because this guy is pushing the signal to 1.5 volt, but I can go ahead and go lower, go to 1 volt peak to peak to make them exactly the same. So now they're 1 volt peak to peak, and you can see the fundamental power. You may not be able to read it, but it's at minus 2.6, but those spurs are still there. Now it could be that some of these intermodulation products, particularly this one, I'm not sure, this is probably some DAC DAC mixing signal perhaps coming out. This is second harmonic right here. So I'm not sure where that one is coming from, but you know, there perhaps something internally causing this tone to appear from the clock DAC combination. But I'm curious now to try something at lower frequency, because it could be sometimes that if the bandwidth, the output driver bandwidth is very much limited in some way, you could actually see artificially an improved performance in THD. So I can go ahead and try that. Let's try it at 75 megahertz or 80, let's try it at 80 megahertz, which is right down the middle, and see and do a comparison like that. So the difference in output power is even greater at 80 megahertz. So at 80 megahertz, I'm still able to get the full 5 volt peak to peak from the instrument that I can set it clearly to 5 volt peak to peak easily. Whereas at 80 megahertz, the Rigol unit is limited to 2.5 volt peak to peak. So it's half as much signal swing, which is quite a big difference. So now you can see that clearly on the oscilloscope, of course, because you can see that on the same vertical scaling, the Rigol output is significantly smaller. So now if I go ahead and look at the spectrum again, you can see that I can actually go ahead and turn these guys, maybe I should just turn both of these channels off, might be a little bit even easier to see. There we go. So now if you look at this like this, you can see clearly that the output power, I have 11 dBm again coming at 80 megahertz. The second harmonic is sitting at -24, and the third harmonic is sitting at -33. So you know, this is not it wouldn't be a fair comparison for me to now go ahead and compare these two signals together, because the output power is so much larger, so much higher from this guy. But anyhow, we're testing it at its maximum. So to be fair, I'm going to go ahead and set the Siglent to 2.5 as well, 2.5 volt peak to peak as well, just like the Rigol is, so that when we do a THD comparison, that it would be fair. Here we go. So under this case, we have this power is now even lower. So we have 4 to 33. Interestingly enough, the second harmonic actually didn't suffer very much. So from 4 to 32, you have about the difference between them. You have about 36 dB of THD. Now I can go ahead back to the Rigol unit to see what its THD is. There you go. So now you can see that on the same settings, they have very, very comparable THD. At about 5 dBm, you're getting -33 at the second harmonic, and at about 5 dBm, you're getting -32 from the Siglent unit. So they're actually quite similar, but of course, at the same time, now the Siglent gives you a lot more output power if you ever need it, which I would take that any day. Because you never know what kind of output power you may need for your application. So now by doubling the signal swing, basically 6 dB, you can see that your second harmonic has gotten worse by more than 6 dB, which makes sense, of course, that's normal. But now you still have about 34, 35 dB of THD here, which as opposed to the 38 when at half the signal. But in terms of THD at lower frequencies, they're comparable, but at 160 megahertz, the signal from the Siglent one has a little bit more harmonics in it, most likely because it has more output actually, more output bandwidth at its two terminals here, and I'll show you that in a different experiment. But in terms of performance, in terms of providing output power, Siglent, no problem. It has significantly more output power than the Rigol does, and their THD is comparable. In some cases, the THD of the Rigol is a little bit better at the very, very high frequencies. But if you need output power, this is your unit. Just for the sake of completion, just to, you know, in case you're interested in this, I'm going to increase the signal I'm going to go ahead and increase the signal from the Siglent unit from 80 megahertz up. Right now it's set to 1.5 volt peak to peak, so you can see the progression of the development of various harmonics in case you're interested in that. So you're 80, now I go every 10 megahertz, and you can see that there's the harmonics, of course, move with it, and occasionally you get extra tones appearing, which are most likely products of the DAC clock in output ratio and so on. So you can probably calculate them by following them if you know the exact clocking frequency. So now we're at 160 megahertz, and that's where you saw the other tones. So in this situation, the Rigol one gives you a cleaner output but at less output power. So you know, you have to choose your battles here. But in terms of signal swing, yeah, I'm impressed with the fact that the Siglent preserves its 5 volt peak to peak signal all the way up to 100 megahertz, which is pretty good. Which is you know, in some cases you have cable losses or you need to put a lot of power. That's the way to do it. Now let's look at some of the other features of these units. Let's look at some of the other arbitrary waveforms that are built into it. So one last thing I wanted to show you is just a comparison of the phase noise between the two units to make sure one of them is not significantly better than the other one. So here I'm showing the phase noise of the Rigol unit first, and remember for this test I have decoupled these two units. They're no longer connected with the 10 MHz reference with respect to each other, so they're running completely on their own internal time base. So I've set the frequency to 80 MHz right down the middle of the full frequency range. The output power is about 5 dBm, and let me just put this guy just to do a few averages here, do a few power averages just so we can see the waveform being more stable. And you can see that with the output power of about 5 dBm, the marker noise density at a 100 kHz offset from the carrier is about minus 101 dBm per hertz, making a phase noise at about minus 106 dBc per hertz. So it's not so bad. It's a little bit more than I would have expected based on the specification for that unit, but we're getting approximately minus. So the only thing you really need to look at is minus 100 dBm per hertz. The reason is because they're set to the same output power, so that way we can just compare the power in a 1 hertz bin at 100 kHz offset from the carrier. This will tell us sufficient amount of information. So I'm going to go ahead and now disconnect the Rigol unit, and I'm going to go ahead and connect the Siglent unit up there. And the reason that doesn't disappear is because it's averaging, of course. I'm going to reset the average afterwards. So here we go. I'm connecting the Siglent unit right there. And I'm going to go ahead and do a clear right again and do a power average again. Here we go. So now it's averaging again. You can see it's about the same. Maybe a tiny bit better, a dBm per hertz better or so, but it's essentially the same value. So you can see that their phase noise is the same, and it's because they're using the same time-based architecture. So naturally they're going to have something, essentially the same performance. I did look at the output swing on both of the datasheets just to make sure to double check. Indeed, the Siglent can give you twice as much signal on a lot of the ranges, especially the higher frequencies. So for output power, I was very impressed that definitely a good bang for the buck there. So what about all the other type of waveforms? Again, this is an arbitrary waveform generator, so you can download your own waveform into it, of course, and I will show you that a bit later. But really, most of the time when you turn it on, you want to do some quick measurement, quick test, you want to use its own built-in function. So aside from the sinusoid, which we've been characterizing and carefully comparing between the two units, obviously has square waves, ramps, and pulses and noise, as well as a DC and an ARP button. And this ARP button can then bring up various built-in arbitrary waveforms, including the ones that you've uploaded into the memory itself. So by pressing that, now you'll get the same kind of settings like amplitude and so on, but you also have this extra button called built-in, and in the built-in buttons you have a whole bunch of different types of waveforms you can load. And you can see the menu, even though, like I said, I was a little bit skeptical about the buttons and the way they were, but it actually works really well. So you can have different things like stare up, stare down, and so on, and different types of trapezoid waveforms, and a whole bunch of math ones which cover things like exponentials and sinks and Gaussians and Lorentz pulses and all those type of different things. And this one they call this project, but cardiac and quake and two tones and signal to noise and so on. So I will show you some of these on the oscilloscope, but there's quite an extensive list. Now, having said that, I have to say that the waveform selection on the Rigol unit is excellent. It has a lot of really complex type of waveforms built into it, which can be very useful depending on the application you're doing. One thing I also really like is the fact that the Rigol unit actually has a harmonic button that can give you multi-tone at the right off the bat. So by pressing that, you can actually tell it how many tones to generate, and it will give you a comb of frequencies. I like that functionality. It can be pretty useful, but you can of course always upload a harmonic type of waveforms yourself, but it's nice that this button is there. As far as I can tell, I couldn't find such a thing with the Siglent one. But it operates on a similar principle. If you go under ARP, you can it's telling you that the waveform was set to 40 megahertz because it cannot do something that is higher than that with built-in functions. You can select the waveform and you can look at the built-in ones, and the list is really extensive. They have a lot of different types of waveforms. You can see maths and trigonometry and medical and bioelectrical and so on, and engine and so on, a whole bunch of different stuff. So it does have a lot of options. So one of the unique features of the Siglent SDG5162 is its ability to generate really narrow pulses independent of the frequency of operation. Now why is that important, or why is that a problem at all? Well, if you think about it, if you want to generate a really low frequency signal, you have a certain number of points that your memory associated with generating that waveform, and then typically what you have is a phase accumulator, like a counter, that grabs the data from the memory and then puts it onto the DAC, and then the DAC will generate the waveform for you. So you can imagine, because the number of waveforms is limited, as you go really low in frequency, you're not going to have many points in the transitions between the waveform, when it, for example, in a square wave, when it goes from low to high. Now as a result of that, what's going to happen is that you're going to get a pulse rise and fall time that's going to be proportional in some way to the frequency that you've chosen. Now what Siglent has done is that they do things differently. They have a special processing unit inside that does this pulse width control independent of the frequency that they're generating. And that's really useful for a few different applications, and I will show you one of those. And it's always beneficial to be able to have completely independent pulse width from frequency of operation. So let me show you that. For example, I can choose pulse here, and you can see the frequency of operation is set to 1 kilohertz. Let's, for example, let's set that to 10 megahertz. And then if I go ahead and let me change the amplitude again, let's say back up to, doesn't matter, 2 volt peak to peak is independent of that as well. And I can go ahead and set the width of the pulse to anything I want, and it will go as low as 6 nanosecond rise and fall time. So I should be able to go all the way down to 12. There you go, so 12 nanoseconds. So now I have a 10 megahertz pulse repetition rate whose width is only 12 nanosecond. Well, that's not bad. Many arbitrary waveform generators can do that, but now what I can do is I can go on the frequency and I can lower this frequency as much as I want. 9, 8, 7, now it's at 1 megahertz. I can even go all the way down to 1 kilohertz, or even below that I can go to 100 hertz. It wouldn't matter. It will constantly preserve this pulse width no matter what frequency I choose. So if I go ahead and go back to 1 kilohertz, let's try and see if we can replicate these settings and then look at them on the oscilloscope for the 2 different models. So now I'm going to go and do exactly the same thing. So remember, 1 kilohertz, 2 volt peak to peak, 12 nanoseconds pulse width, and see if it can be done. Alright, so here we go. Let's go ahead and try that. Let me lower this guy so you can see a little bit better what I'm doing. So let's choose pulse, like that. And let's go ahead and change the amplitude to 2 volt peak to peak. It doesn't matter, but just for sake of consistency. And I can go ahead and change the frequency. First, let's start like we did before with 10 megahertz, like so. And we can go ahead and try, and you can see it already changed the pulse width limit. So you can go ahead under the leading edge, make sure that's, I just type 0 so I can minimize it. So there you go, it's now set to 5 nanosecond as the leading edge of the pulse. And I can go ahead and change the width to, in terms of nanoseconds, and again I'm going to enter 0 just so we can see the minimum. There you go, 10 nanoseconds. So this is a really narrow pulse now. It's 10 nanoseconds width, and the lead is only 5 nanoseconds. So it's actually smaller right now than what the Siglent can do. But look, if I go ahead on the frequency, and I'm going to go ahead and lower the frequency, keep going down to 1. Now it's 1 megahertz. There you go, see? It already changed. So it says other parameters were modified to meet this new setting. So as soon as I went below a couple of 100 kilohertz, it can no longer do the width of the signal that it had before. It had to change it in order to be able to meet that. So now if I go to 1 kilohertz, like so, under 1 kilohertz, the width of the pulse is now significantly higher than what the Rigol can, the Siglent can do. So I'm going to go ahead and try again. I'm going to enter 0. So now I can see that it's the lowest value is 3.125 microsecond, and as well as the leading. I'm going to also do that, and you can see that it's, the lowest value you can do is 1.95 microseconds. So at this exact same configuration, you may be, they're quite competitive at higher frequencies because the pulse width can be made even a little bit smaller on the Rigol, but it can generate really small pulses in both cases. But as soon as you go in low in frequency, now the pulse width is significantly limited. And just to give you an idea of how different these two are, let's look at them on the oscilloscope so you can get an exact direct comparison. There we go. You may be wondering what you're looking at. So here is the pulse from the Rigol unit. You can clearly see it, but the pulse from the Siglent is so small that it is buried in this axis. That's how small that pulse is, but I know it's there because you can see the triggering is happening at 1 kilohertz, and I can do a single trigger, for example, like so, and then we can zoom in, and then you can see eventually the pulse from the other signal. But you can see how much larger the other pulses are compared to the pulse from the Siglent unit. Now, of course, if I increase eventually you will see all the tones from all the signals. So now I can go ahead. Let me go ahead and slowly bring this to the center by adjusting the phase of channel 1, and this will allow us to align them together so you can see them very well. So let me go ahead and change the starting phase. Let's see if I put 10 degrees. Okay, it's going that way, but that's okay. Eventually another one will show up. There it is. There we go. So now we can do some fine adjustment. Now I can zoom in a bit more, but you can see clearly the difference. There you go. I can put it here. Oh, there you can see that. You can see how they're actually not locked. I forgot to lock them back with respect to each other. So let me go ahead and make that change. There we go. I enabled the external reference. So now I can move this guy into view. So there, I'm going to put it in the center. So again, you can see there. Now you're beginning to see it. There it is. You can see the individual steps of the DAC that is coming out of the Rigol unit, but look at the difference in the pulse width. I mean, it's not even in the same league, of course, because Siglent has this special extra DSP processing that they do on the pulses to modify the width of the pulse independent of the frequency. Of course, if I go up in frequency, then it will be a different story. That will become more comparable. So let's try this at 10 megahertz, for example. So I'm going to go ahead and choose this to be 10 megahertz. I'm going to change the frequency of repetition to 10 megahertz, like so. I will fix the scope in just a second. There you go. Now I can go ahead and adjust this as well. Oops, wrong button. There we go. We can go ahead and set this guy to 10 megahertz as well. And going back between the two UIs, you have to think in two places at the same time. Here we go. 10 megahertz. So it changed our pulse widths and so on. So I'm going to go ahead and make this as small as it can be. There you go. Now 10. I'm going to change the leading edge to, there we go. This is as small as it can be. So at 10 megahertz, they're much more competitive. There you go. Let's take a look. Let's change the time base. There you go. There you go. You can see they're much more competitive. At 10 megahertz, they're essentially the same. The Rigol has a small advantage here. You can make slightly smaller pulses. It's 10 nanoseconds as opposed to 12 nanoseconds, and I can go ahead and change the start phase, so trying to align them as much as possible so you guys can see better. There we go, almost. There it is. So you can see if I align one of the edges that there's a tiny advantage to the signal coming from the Rigol. But again, you can see the difference is at lower frequency. So I've devised a little experiment to see how this can be used to our advantage. So here I built a really simple circuit. It's two salient second order filters followed by another one. So I have a low pass filter followed by a high pass filter with a particular value of components to give us some reasonable frequency response and so on. So what you expect is a band pass response from the combination of these two type of filters, and you can see it's assembled on the breadboard here. And the reason I want to show you this is because I want to show you one thing you can do with being able to generate independently narrow pulses from the frequency perspective. So normally if you want to measure a frequency domain of something like this, you either need a tracking generator, or if you're doing very high frequency or very fancy stuff, you would need a spectrum network analyzer. But if not, you would essentially put a tone at the input and then measure the output tone peak to peak value, and then you change the tone frequency until your output signal peak to peak drops by 3 dB, and that will be a 3 dB frequency. But there is a way where you can excite this circuit with a broadband spectrum and then look at the frequency shape at the output, and that will give you all the information you need about that. And as if you remember in one of my previous videos, I talked about how generating really small impulses, the duality between an impulse train in the frequency domain and the time domain, and we said that frequency domain, time domain duality means that the impulse train is actually the same in both domains. So an impulse train in the time domain is an impulse train in the frequency domain. So therefore, by being able to generate very, very small pulses, you're generating a really broadband signal. And you can feed that to the input of your circuit and then get a frequency response. If you want to get more information about that, it doesn't really belong in this video, but you can go ahead and look at my repair video of my frequency counter where I talk about that in detail with regards to a step recovery diode. So anyhow, so here what I've done is that I am generating a really narrow train of pulses and it's being fed to the circuit. So I'm just looking at it here on the oscilloscope. You can see there my pulses are very, very small, and you can see them right there. I can change the frequency. You can see that here's an example of one of the pulses. So I'm going to feed that into my little op-amp circuit, and my op-amp is being powered by a Rigol power supply here, the DP1308A. So I'm just powering it from plus or minus 10 volts. And here you can see that the Siglent arbitrary waveform generator is set to 250 kilohertz with the narrowest pulses of 12 nanoseconds. So it all looks nice and everything. So I fed it into the circuit, and then we can also look at what comes out of the circuit. It's going to be also a train of pulses, but there's going to be some dispersion associated with that as the signal goes through and is low pass filtered by the circuit itself. So again, I'm going to show you that in more detail. So let's go ahead and look at this in the frequency domain. And in order to do that, I'm going to use a passive probe, but which is matched to 50 ohms. Actually, this is a 500 to 50 ohm transition. It's a 10-to-1 probe, so its output impedance is 50. It's 500 and its input impedance is 50. So what it means that I can connect it directly to the spectrum, into the spectrum analyzer input, which you normally cannot do. So you can't just connect a passive probe to 50 ohm unless it's designed for it. So let me go ahead and do that, and we can take a look and see what happens. So let's first take a look at our input signal. Here we go. I'm connecting this guy, which is my spectrum analyzer input, here, like so. And we can go ahead and analyze this signal in the frequency domain. Alright, so here we go. Now you can see, and I'll explain what it is exactly that we're looking at, and you can see the duality really clearly. So here my impulse train is at 250 kilohertz repetition rate, and its pulse width is minimum only 12 nanoseconds. So these tones, these many harmonics that you see here, are at 250 kilohertz separation, as is to be expected from the impulse train. Now, the whole impulse train I'm showing from 0 Hz to 50 megahertz. So it's going to itself have a sync behavior, and that sync shape of the impulse train is because the pulse width is finite, it's not infinitely small. So if I go ahead, for example, and change the impulse width, you can see what happens. So I'm going to go ahead and increase the impulse width, and you can see that the sync function moves in. And now it's too much signal, so let's set that back to 0 dBm, so that goes away. There you go. Now you can see, so this, the point of the sync function, the null of the sync function can be moved around by changing the width of the pulses. If the pulses are really wide, like for example right now I have a pulse of let's make it 200. There you go. So this is a 200 nanosecond pulse. Even though the rise time is still extremely small, you can see, here's my pulse. You can see the pulse right now, then there it is. You can see it's much larger than it was before. You can see the shape of the sync function here. So now this is not flat anymore over the frequency range we're interested in. That's the problem. If I want to measure the frequency response of something, let's say I want to measure the frequency response of something up to 10 megahertz, let's go ahead and set the stop frequency at 10 megahertz, like that. You can see that up to 10 megahertz, I actually already have a null in there. So that's not going to be very beneficial. But because I can make the pulses really small, look what happens. I'm going to make the pulses tiny. And look, as far as we are concerned, in the range that we are interested in looking at, this is essentially flat. So now this has a very flat frequency response. I can actually feed that into my circuit, and then I will be able to see the shape of the frequency response of the circuit instead of seeing the shape of the frequency response of the instrument, and that's why I am able to measure that. So I can go ahead and make the frequency repetition rate even smaller, and you will see that the pulses will move closer to each other, like so. But the nice thing about it is that this will remain completely flat because I have a complete independent relationship between the pulse width and pulse repetition. So now we can go ahead and look at the output of the circuit versus the input of the circuit. So here you go, here's the output. You can see it in the time domain. Much easier. Here's my pulse at the input and output. Now if I go ahead and take the probe from here and connect the probe to the first output, so this is now the high pass, the low pass signal, like so, and we can go ahead and look here, and you can see that already there is a roll off of the frequency response of the circuit itself. So let's go ahead a little bit further in frequency. Let's stop at 20 megahertz, like so. There you go. This shape that you see is now the shape, the frequency response of my circuit, and not the frequency response of the instrument. So again, I'm going to go back to the input. So here is the input. You can see that is mostly flat. I can even make it more flat by changing the width to be smaller. There you go. Now I can go ahead and look at the output of the circuit, like so. There you go. Now you can see clearly the 3 dB frequency, and if you were to measure that 3 dB frequency, I did that and it matches perfectly to the component values that I've selected. So now you can see the frequency response of the circuit. Now I also have a high pass, so I can go to the output, the final output of the circuit. There you go. And this is the frequency response of my circuit. Now you wouldn't be able to do this. You would have to take many measurements in order for you to be able to see that. So I can even go ahead and make this a little bit more clear for you. This is gonna, it always takes a bit of getting used to. I always forget which knob does what. There you go. This is fine. There you go. There it is. So now you can see clearly the frequency response of the circuit. Remember I told you this is a low pass followed by a high pass. So here's the high pass response, and followed by a low pass response. So then now you get tons of information. For example, now I know that the isolation of the Salem key 2 stage filter is actually not very much. So this frequency, this filter doesn't have a lot of rejection at higher frequencies. It would take a very long time to measure by hand if you didn't have a tracking generator. So you can see a very basic function and a very basic advantage. Again, I'm going to go back to the input just so you can see this is the output of the circuit, and this is the input of the circuit. And the difference between the two of those is, of course, is going to be our frequency response. There it is. So now you can have a pretty good idea of what you can do with really narrow pulses. It's just one example, and there's other things you can do. For example, if you want to measure independently of the repetition rate, the rise and fall times of digital circuits, or the rejection of a digital circuit to a very narrow pulse in some scenarios, if you have AC coupling and other things like that, then you can use this really narrow pulse, which would be advantageous. So in an AC coupling scenario, the DC will not go through, of course, so the low repetition rate becomes really important, but the narrow pulses will go through, so you can test AC coupling behavior of your circuits by having this pulse, and you can inject noises into your power supply this way. There's a lot of fancy things you can do, being able to have completely independent control between pulse width and repetition rate. So as one last thing I wanted to show you is the EasyWave software that's available for free for the SDG5162 from Siglent, and you can do a whole bunch of different things. You can generate waveforms really easily. It's a very simple software, but it's also really easy to use. I was happy with it. I was playing around with it a little bit before for a couple of days, and you can generate a whole bunch of different waveforms. You can hand draw, you can draw by a polynomial, by math function from a table, so you can make a waveform really easily and then upload it. And all you do is just click on send wave, and then you choose the waveform that you have chosen, and then you just select the channel and you upload, and that's it. And you can save it into any of the available slots depending on how much memory you've chosen to occupy, and then you can save many waveforms, and they will stay in there. So you can, if you have some waveform that you want to continuously work with, you can generate a whole bunch and then upload them and then have them in your unit. So it's really nice to use. So there you go. Here's here's an example. On channel 1 I've just done some hand-drawn waveform, and on channel 2 I've done some linear waveform. and I've already uploaded them to the unit. So let me go ahead and show you. This may look like it's nothing, but it's actually something that I tried to do. I tried to do it for 10-15 minutes by hand, but anyhow, you'll see what I mean. So let's go ahead into the unit and take a look and see how that looks like on the instrument. So once you upload the waveform, it actually shows you that waveform. If you remember, this is what I drew on one of the channels, and if I go to the other channel, that's the other waveform that I drew. So it actually shows you what waveform is going to appear on the oscilloscope or from the output of the unit. So it's pretty nice, you know, it's very easy. It had no problem doing this. I connected it to the USB, ran the software, and it all worked out. So here it is. I have it here showing on the oscilloscope. There are my two waveforms that I had drawn. You can see them. You know, they're being displayed really nicely, very easily. So, well, what I was actually trying to do was I was trying to draw something for you guys, but anyhow, it wasn't very easy. So let me show you what I tried to draw at least. I'm going to put this into XY mode. There it is. It was supposed to be an umbrella. It's kind of an umbrella, I guess. I mean, for something being hand-drawn, it's not too bad. So there you go. So you can this is the of course X versus Y. So on this axis you got one of the waveforms, and then the other axis you got the other ones, channel 1 versus channel 2. So there you go. You can see it's a really poorly drawn umbrella, but not too bad for something that's drawn on the screen. So you can see that, you know, it's really easy. It took me literally 1 minute to get all of this thing going, and then it works really, really well. And you know, there's a lot of other stuff that I can show you, but this video has already become quite long. You know, these instruments support modulations and sweep and burst mode operations, and there's a whole bunch of the stuff you can do, of course, with those. Now, I haven't gone into the detail of all those stuff yet, but it's quite capable. You can even modulate your arbitrary waveform generator, of course, with FM and AM modulation, and create really complex and interesting waveforms for different applications. I will in the future use this unit because I really like the way it works. You know, I also really like the Rigol one, of course, but I think that there's a lot of cool things, neat things you can do with these units, and I will get into it. And of course, as I said, I do have the Siglent SDG5000, which is a 5.5 digit meter, and I will review it. I will do a teardown with it. I will stress it and put it through, you know, its paces. But let me know if you have any questions about it, or if something you want me to test. Definitely, we'll do that for you guys. And as always, the only thing I ask you to do, you know, leave a comment. Let's get a discussion going. If you like the video, give it a thumbs up. If you do happen to purchase these because anything that I review, because you've seen me review it on there and you like its features and so on, let the manufacturer know that you saw my video, because it keeps a good relationship between me and them, allows me to get equipment for you guys and do reviews and teardowns in the future. It's just it will take only a couple of minutes of your time, and it will help me greatly to bring you this type of content. In terms of whether you should buy the Siglent or Rigol, really I have absolutely no brand loyalty. As you know, here we've used multiple different types of instruments just to test these things, so it's really up to you. You see it, when you see me test it, you see me measure it, you look at the response, you look at the EUI, you look at the performance, and then you decide what will suit your needs. The Siglent 5162 is about $300, I believe, cheaper, $300 or $400 cheaper than the Rigol one, so it is a cheaper unit, but you know, it has its disadvantages and it has its advantages. For performance, I like the Siglent quite a bit because it can do some of the niche little things that can be quite beneficial. The Rigol one might give you a bit more features and so on. So I'll leave that up to you to decide which one you like to have, and you know, we can discuss further things if you have more questions about these units. Since I have them here, I can experiment in them for you guys. So I hope you enjoy this. Until next time.